this presentation is kind of about, I mean, a little bit off topic from what you'd see in the programme, but I think it's worth, I think it's quite an interesting presentation, but not necessarily what you expect. This came about out of, this is such an emerging excitement about synthetic data and what it can do, and I kind of felt like I got a broad understanding of the industry, what people are doing, but I had no idea actually what you could do with synthetic data, and realised there was a bit of a dearth of information about how well different synthetic data techniques work, and so this was just a story of my exploration of this topic. I'm not a machine learning expert. I'm just a regular researcher, and everything I'm presenting here is actually created by our machine learning team rather than myself. So don't interrogate me too much on the detail. Now, the two types of synthetic data that everyone's getting excited about, there's large language model stuff, which is probably the more sexy stuff. And then AI machine learning techniques to impute enhanced data. That's the bit I've been looking at, which is probably a little bit more nerdy. There's a wonderful MRS Delphi report that looks at the applications of synthetic data, and the one thing that's identified is the opportunity to essentially boost sample using synthetic data, and that's the focus of what I've been looking at. And so what I've embarked on the last probably about 4 or 5 months is a series of experiments to test out different synthetic data generation machine learning techniques using a variety of research data sets to see how good they are, and looking at their ability to augment, ascribe data, and then full-blown sample boosting, reproducing a whole survey. And what I've been looking at is how good these different techniques are. The new generation of machine learning methodologies, how good are they compared to some of the old school methods? But probably more fundamentally, what factors impact on the quality of synthetic data? As a researcher, that's the bit I'm probably most interested in. And if you are going to think about using synthetic data, what are the critical considerations for planning and using it? So there's all manner of different ways you can create synthetic data from machine learning. These are just some of the ones that we've been looking at: logistic regression, random forest, some of the various nearest neighbors methods, gradient boosting, neural network. This is all jargon. I don't know whether you can come and I just try to explain all these, but I think I might get tied up in knots. But these are basically, you start off with the classic regression. Random forest is a long-established method where you select a cluster of data and try to make an imputation, and then just randomly makes a prediction and you aggregate those. Nearest neighbor approaches is basically looking for a similar respondent and then imputing their answers. There's a technique called SMOKE, which is called minority undersampling, where basically to deal with the fact that if 90% of people say yes to something, the nearest neighbor is most likely to say yes, so you have to think about how you balance for that. Gradient boosting is a technique where it makes a prediction and then examines how far out it is and then tries to revise the prediction and does it in a loop until it gets something it thinks is okay. The neural network analysis stuff, the deep learning, is the sort of stuff that all the big boys use to do more complicated analysis. It's not using traditional regression sort of correlation analysis. It's looking for shapes and patterns of answers that can be reproducible. So it doesn't start with assuming it's a straight line relationship, which has its strengths and obviously has its weaknesses when you're talking about different scales of data. Now, there are a couple of quite hybrid methods emerging. There's lots of libraries of slightly more advanced methods that combine some of these things, and ensemble methods that basically put loads of different techniques into a pot and come up with a generalized answer. And then the hot thing that everyone, if you dig into it, is the technical GAN, which is, I think, generative adversarial networks. It basically is a way of imputing. It's basically a form of deep learning that imputes a whole survey. We've looked at that. And there's also things called variational autocoders, which I don't really quite understand, but our team are looking at the moment. So what I did is I took a cross-section of different surveys and as a sort of training set to look at, the boundaries of this topic. I took a classical brand tracker that we had at Kantar with couple of years worth of data, 25,000 responses. We've got a massive cognitive profiler, which has got loads of questions, so we've got lots of columns of information to look at the value of adding more and more features to a prediction process. We've also got a survey we developed to test the quality of sample with a whole load of archetypal research questions alongside a range of quality control questions that test essentially the how trap questions, and we measure straight lining activity and so on. We assess the quality of the respondents. I thought it would be an interesting way to then compare good and bad quality respondents using that data. And then I took some data from one of the honesty priming experiments I was doing. I was trying to work out how to get people to be more honest about things like voting. And I put people through a series of priming process to get them to be more truthful. And I then looked at how well I could model the untruthful group with a truthful data set. So that's the sort of thing I was working with. And what I then did is I wanted to compare how well can you compute data from surveys with different quality sample sizes, and then how well you can impute data from different types of questions, not just the whole survey, looking at the added value of adding more profiling information to how does that improve the imputability of the data, and the impact that the quality of the responses had. And this is a bit of jargon. I compared, by and large, the accuracy and precision of the answers. And there's, if I say, for example, I can predict pet fish ownership with an incidence rate of 5% with 90% accuracy, that means I'm only about 50% precise, because I've only getting half of them right. So those two things is important. Precision is probably more relevant than accuracy. There's another thing called recall, and you can, these machine learning models also pick out, a number of false positives, false negatives, stuff like that. There's loads of data they generate. So probably the key questions you've got is how good are these different techniques? How good are some of these more advanced new methods compared to old school regression and random forest? Well, for my experiments, it all looks to be a bit of a muchness. Yes, some of the new techniques are slightly better, but not significantly so. If I move from logistic regression to random forest, I can see a leap, but when I move to things like gradient boosting and some more advanced hybrid regression, they're only delivering, 3 or 4% improvements in accuracy. There was a difference in precision. The one that stands out here is nearest neighbor using the smoked minority oversampling on smaller sample sizes. The precision there is actually the fact that it's actually just copying the original data, so it's really just a form of weighting, frankly. But all the others are kind of along the line. The one you'll notice is the worst performing on a typical survey is neural network, deep neural network, because it simply just doesn't have enough data to make the connections with. And then when I look at how you can impute the accuracy of different types of questions, there is a massive spectrum of performance. At the one end, if I've got 10,000 responses to a brand tracker, I can predict with nearly 90% precision the answers people are going to give to an image statement question. That's probably more a fault of the survey and the patternized answers that people give. But you may as well not bother asking the question because you can impute it so accurately. To the far end, I took an example where there's interesting work looking at how well personality predicts birth order, and it doesn't. I mean, particularly middle children. You cannot predict someone's personality by their birth order. And it's true, none of the models could pick up an indication of whether you're a middle child or not. And so its precision is very poor. And everywhere in between, gender, if I add in, trying to predict gender from a personality test, there's loads of little indicators to determine whether you're likely to be a man or a woman, so that could be predicted very well. On the same personality test, trying to predict if someone drinks red wine, it can't do it quite so accurately because there's not so many linkages for the data to process on. So what you realize is that you cannot talk generalized about how good is synthetic data at generating data. You have to think about individual questions, how good is, and what is the information within the question that enables you for the model to work off to make that modeling process. There is clearly, the more data you throw at it, the more accurate the models become. Neural networks start to kick in competitively at about 10,000 responses. And I didn't have a big enough data set, but I'm sure it overtakes when you start to reach about 100,000. But you can see they're all kind of reached the same sort of ceiling point. And that, that was probably my biggest learning from this, is that all this fancy technology and all these new techniques, they don't really do much better than old school regression, frankly, because what they're doing is they're finding is the quality of the training data is the issue. So there is two ways you can improve the predictability of a model. You can add loads more rows of data, but you can also go this way and add more and more features and add in more questions. And so what I looked at, I did some experiments where I would isolate some of the demographic information and then compare it with and without the demographics. And what you can see is you do get a bump from adding demographics often. This is I compared some deep profiling of a survey with and without adding extra information. You get a better prediction. But going that way is quite idiosyncratic, because take, for example, I'm trying to predict whether you use makeup or not, or trying to predict whether you've got a dog or not. And if I add these 3 data points, your age, gender, and region, well, makeup precision gets boosted up simply because only half the population tend to wear makeup, and there's an age difference, and there's probably some slight regional differences. So adding just those 3 data points significantly improves my precision of predicting whether you wear makeup or not. It's kind of obvious. But it does nothing to improve my prediction of dog ownership, because it's so homogenized, dog ownership, around the population. There's nothing that those data points don't actually add any value. So what you have is that adding more and more stuff that way, randomly you might hit the jackpot and finding something that's connected and you'll get a boost, but sometimes you won't. And the other challenge you face is that the more data points you go that way, the more noise you're creating, and you can actually just see your precision sort of falling off a little bit, because it starts to sort of find these phantom things and sort of like completely pollutes the modelling process. So going that way becomes problematic unless you've got some very, very strong internal relationships in the data that's worth exploring. So then the next question is, what impact does the quality of the responses have on the quality of precision? And again, there is a bit of a boost. When I took my sample survey and I divided it up into thirds, and I took the highest third and the smallest third, and there is a boost, but on a typical survey, it's not perhaps as much as I'd rather hope for, and I'll talk about this in a bit. Irony is that you can model poorer data sometimes a bit more reliably than better quality data, because there's more patternization of their answers. But it's not necessarily better modeled data. It's just you're just finding the fact that it's feeding on itself in a sense. What I've found in actual fact is that, let's talk about this. The honesty of the responses is critical. So if I'm trying to predict whether you vote or not, and in the non-honesty prime survey, 80% of people were telling me that they voted, where I know it's only about 57% of the UK population. The predictability of that is really difficult, because there's just a load of noise in there. But with a more honesty prime group, where I was actually in the survey itself, I was able to get a prediction of how many people voted very close to the actual number. That data was so much more modelable, because it was true, and so you want less noise in the data. To the point where you constantly, I found this good one, where the models pick up on untruthfulness in a sense. This is one on one survey I analysed where I noticed that the precision with which age could be predicted for younger age groups was much better than the precision for older age groups. And we've got a generic problem with older people taking surveys is they're constantly screened out. And if I click the 55 plus button, I lose my place in the survey and I get... So older people on our panel, we've noticed it separately, are starting to pretend to be younger. So they get through to the survey. And this is, almost being revealed by this modelling process going wrong in the older age group. When you actually look at the underclaim on age is a lot better, a lot higher on the older age groups than the younger age groups. And when you look under the bonnet, there are gaps. The higher age group are even more significant. So what we're having here is a classic case of the model data is potentially better than the real data, in a sense, because it's actually highlighting a bit of a dishonesty amongst the respondents. The next thing we started to do was try and look under the bonnet of some of these predictions using a technique called Shapley analysis. It's a technique. Now, this can only handle certain types of model data, so you can't use this technique very well for neural network analysis, but the other models were able to have a look at some of the underlying connections, and I found this very useful way to compare the ability to model data is essentially how consistent are the model's prediction, what are they based upon, what features are each of the models based upon, and take a question like gender. You can see that all the models are fairly stable. They've got similar questions that are driving the prediction. I'm fairly confident in these models' prediction of gender. With red wine, again, quite stable, but a little bit more variance. Owning a dog and a cat and not playing computer games and income and watching sport all seem to contribute to your preference for red wine. Not necessarily obvious things, but they're revealed by that process. But this is the model's attempt at explaining why someone might be a middle child. You get total chaos between models. Every model comes up with a different answer because what they're doing is just finding phantom connections that don't exist. And this is a real challenge. What I would do is I would then repeat the modeling process with another random set of data, and the answers would change again even further. So looking at the changes in behavior and the changes in predictions is a really good way of testing out the validity of the modeling processes, whether you can actually impute any data from the data set you're working with or not. And what we found, generally speaking, when you're working with small samples of about 600 responses, which is actually a typical survey, nearly all the models started to get a bit wobbly, particularly when you repeat process it. And you found that I became a lot less, what's the precision looked like on paper, it was okay. It was basically essentially overfitting the answers. And so that became a bit of a worry to me. And then when I looked at the differences in poor quality sample and quality sample, whilst the precision of poor quality was in line with quality samples, what they were based upon were completely different. So this is poor quality sample, how it made its prediction. It was all based upon self-referenced answers around the same question. And essentially, it was basically picking up on the patternized behavior of someone's response to the survey, not actually basing it on real insights about the real connection. So I think, highlights a real challenge there. And then obviously we have the real obvious potential for these types of models to bake in bias. So I've got this wonderful way of predicting whether you're a man or a woman with 80% accuracy, which sounds really great, but what if I'm a woman who likes sport and beer, or a man who likes shopping and reading? All of a sudden, the system now thinks I'm a woman or a man. And so that's the challenges with all this. And then these things have no differentiation between causality and correlation. We were doing some wonderful work a couple of years back looking at trying to predict, what made people happy. And we found this wonderful connection between owning stuff like an air fryer and happiness. But what we also discovered that was a massive correlation between overclaiming, owning stuff, and happiness. And when you rebalanced that out, you ended up, eradicating, there was no relationship. And so what you realize is that all these models basically look for correlations, not causes, and probably that tees up Frank's presentation tomorrow is going to talk about all this, how do you find the cause rather than the correlation, because that's a really critical thing. And so, in summary, whilst these new techniques are a little bit better, the old school techniques, they're only marginally better. The limitations of all this really centers around the quality of the training data you're using. So, there is an argument that you can sample boost if you've got a shed load of data from a big tracker and do the type of things that YouGov do with the MRP style technique to regress and apply a model. And yes, if you've got a lot of data, sample boosting is potentially an option. In the middle zone, you might think about it as a bit of a fancy weighting process, but with problems that you probably haven't thought about to do with overfitting and overclaim and the causal relationships that the models are actually making its conclusions about. And at worst, has the capability of overfitting your data, totally corrupting your insights and amplifying the errors that are sitting within your data set. And so I think the research industry needs to think really cautiously about the capabilities of synthetic sampling. The viability of sample boosting really depends on the amount of training data and the internal relationships you have on any one survey with one question and another. So it needs to be assessed at a case-by-case level, a question-by-question level, not a collective level. And it's very dangerous to think about the accuracies of synthetic data in general terms, in my opinion. So these are some, if you're going to think about using this is a list of critical questions I've made up that you can think about asking someone. What methods you're using? What's the size of the training set? You're synthesizing from? What's the depth of profiling information you're using to model from? How accurate and precise the predictions? Not at a survey level, an individual question level. How stable and reproducible are the predictions when you rerun them? What are the underlying features of the prediction models? Are they stable run to run? How self-referencing are they, which is a really critical question. Do they pass a real common sense check? Are you sure they're causal, not just correlating factors? I think that if we're going to think about AI, as market researchers, we just can't. AI in itself means nothing. We need explainable AI as market researchers, and that's what we should be thinking about driving towards. And there's some, out of these experiments, loads of generalized learnings. What I learned from this is how important the pre-processing of data is. How ensuring you normalizing all the responses, removing outliers, breaking out non-orderable data variables that don't necessarily have a scale relationship. The techniques of things like minority oversampling are really critical for certain types of techniques, and if you don't use it, they just produce nonsense data. And so that requires some skill and knowledge. Things like parameter tuning, there's some other things. So this is not stuff that the average, does take an degree of expertise on. I'm certainly not one of those myself. And there is the other thing that actually was, you were talking about this general challenge of ordinal data. It's rubbish at it. It's really great this is trying to predict scales. It's really okay. It's okay at the top and the bottom end of the scale predictions, but the precision of mid-scale points is really poor. In every single experiment I ever did, it can never really get that middle ground very well, because by and large, because the way that people respond to those types of questions, it's so patternized and there's no signal in that, which is actually an underlying problem of market research, actually. But that's me. I sort of rush through this. I don't know.
Rubbish. Absolute rubbish.
JT?
Frank. You'll be next. Sorry, JT, I'll get you first.
John, fantastic as always, and thank you for your transparency with all this great work. I had a question for you. You talked about creating data sets that are more predictive, adding rows and adding columns. Adding rows is great for us all. More surveys, please, more good quality surveys. Adding columns, it reminds me of picking really good segmentation questions, doing good research to key driver analysis. Is it similar to that? Could we pick better questions?
Yeah, I mean, if I were to take the analogy of my experience of predicting fantasy football results, there are about 1 billion different ways you can predict the performance of a footballer based upon the number of touches they have, the average time they spend on the opposition side, how many shots they have, and so on. And for many years, people tried to make sense of all that and with loads of columns of data and tried to make predictions. And what they were creating is homogenized random mess of a noisy sort of prediction. And what they settled on was isolating the most predictive measure, which was XG, and focusing on that and dropping out all the other noise because it was just creating messing. And what they then realized is that to make a prediction, you then had to add in completely independent variables, like, for example, the predicting performance of players, not just about how good they are, it's who they're playing against. So adding in a new dimension of information. And so simplifying it, broadening out the insights, adding in more relevant variables. So that that's a researcher's job to try and identify those. And once you've got that framework, you can potentially produce some very tailor-made research solutions that are potentially a lot more predictive. But it requires a lot of work.
Thank you, John, for this wonderful talk. As I understood, is what you did, you compared different imputation methods. So, but when we talk about synthetic data and boosting, I think about imputing cases 100% synthetic, which is not imputing. Because with imputing, you use information of a person to predict other variables, which are missing. So boosting for me is like imputing and generating cases that are not there. So for this type of data generation, you cannot even use prediction or accuracy methods. You would rather generate those data and try to see whether or not, for instance, predictive methods produce similar results on synthetic and on real data. Just to close my thoughts. So I also agree that synthetic modeling is like a perpetuum mobile, right? You will not produce new information, right? That's the hope, right? You put it in the machine and it will produce more information, but actually the boosted data it could generate depends on the information you put in, right? And so my question is this pure boosting? Is it what you analyzed, or
you can actually, if you think about it, what I'm doing is like slow-mo analysis of an individual question. But in theory, you can imagine I've got a whole load of existing data, and what I want to do is produce a copy of that data. I can do it row by column by column, predicting each question in a new synthetic form, and it lie it out that way. And then I've got an absolute, using all these different techniques, I then have a synthetic copy. So you can use these essentially imputational techniques to do it that way. But generally, the techniques that tend to be popular, like for example, GAN, will do the whole thing shebang all in one go in an invisible way that's almost impossible to analyze and understand.
Yeah,
so that's why I've done it. That's why I've done it on this particular blow-by-blow way, really just to understand actually, with data it actually knows the answer to, how well it can predict it. But I take your point.
Yeah, I think that it's a good analysis what you did, but how I understand these boosting methods is they are not a dependency analysis like logistic regression. So they model the density of the input space and basically sample this density, multidimensional density space, to create samples that are from the similar density, right?
Yeah.
But are different.
Yeah.
And the ultimate validation would be to take them to the test and see if relationships, so driver analysis and so, would reveal the similar results.
Yeah.
If this is successful, it's a useful boosting. If not, it's just another noise you create.
Yeah. Yeah.
Again, so along those lines, I've done some experimenting, and you can go on GitHub. YData, for example, has a good GAN tool that's open source, right? Oh, sorry. Has a good tool that's open source on there. And with GAN, you can create, so yeah, it's one thing to go, question by question, but with that, I've run synthetic respondents to augment and then done segmentation, right, to see, okay, do we have actual coherent respondents? And it actually does line up. So, I mean, you can see that you do have what I would call a coherent copy of a particular individual. So you could then, let's say, do k-means on that cluster and you basically augmented your personas. But that said, I'm still not convinced that I couldn't just multiply the original data by however much I want, right, and kind of get to the same point. So, but there is a coherency, in some methods.
I accept that, but it is essentially you're copying the original, essentially.
Well, right, yeah.
Which is waiting.
Yeah, that's what I'm saying. I was like, you can do it, but it's like, is it?
Just one quick question by Oken, and we have to stop. Short answer, John.
But it can be a long question. So it goes a bit in the same direction. Just I understood you didn't analyze it that way, but you mentioned or you showed that the data size, how much data you already have, is really relevant to that the model works. But the promise of these kind of tools is often that to when you can't get enough sample, it's, for example, to boost niche target groups, etc. And then did you analyze, or what do you think about how realistic it is if you in a survey you only had 20 people and you're trying to apply these kind of techniques to improve, to create synthetic rows on such a small sample?
It becomes, I mean, for the reasons I explained, it becomes very difficult unless you can just do essentially a copying protocol and try and mirror it in terms of, without any modelling at all. I mean, there is an argument to say that you smooth out individual respondent errors. There is an argument for that. I can get that, and so you're basically ironing out outlier factors. But it's just feeding on itself, and unless you can actually find all the real modelable connections, it's just reproducing the same noise.
But when you say it reduces the outliers, but it also reduces the variance.
Yeah, and I think it comes with its own problems, and I don't know that it's a solution to a problem you're trying to solve, which is trying to make up for missing data.
Thank you. See you next time.